In this lab, we'll be dealing with the magnetic field of a bark magnet. The purpose of this lab is to measure the distance-dependent magnetic field of a small bark magnet. In this lab, we will compare the on-axis and off-axis magnetic field found through calculations and those through computational model. In the result, we found that N was equal to negative 2.873 and the magnetic dipole moment was 3.58. Here are some fundamental principles that we need to understand. The Van law states that a moving electric current produces a magnetic field, and it lets us calculate the strength and direction of that field at any point in space based on the current, distance, and geometry of the conductor. The formula for that law is right below its definition. And using that formula, we are able to calculate the magnetic field of a dipole, which is that formula. And then the distance dependence formula states that as distance increases, the strength of the magnetic field decreases. And these are the two formulas that we are using to show that. Here are the procedures for this lab. The system is the magnetometer and the surrounding is the bar magnet and everything else. Step 1 is to find the location of the magnetometer chip on the phone and orient the phone towards the north to account for the Earth's magnetic field. Step 2 is measure the distance between the magnetometer and the bar magnet for the on-axis direction and the 45 degrees direction. Step 3 is using the data we are going to calculate the magnetic dipole moment. And then step 4 is using the magnetic dipole moment, we're going to create a computational model for the magnetic field of a dipole in GlowScript. And here's the result of the data collection. On the top is the magnetic field and the distances of the bar magnet when it was on axis. On the bottom is when it was off axis, which includes the x and y direction. On the top, it includes a graph where the best fit line of the graph allows us to find n and k. On the bottom, I found that the d-perp, which is the distance of the x and y needed for the net magnetic field on the magnetometer to be around 10 was 0.1955 meters. Here are the calculations needed to find the magnetic dipole moment. Y is equal to negative 2.873 for x minus 14.149, which is given from the data collection on the previous slide. Using that, we know that n is equal to the slope of that best fit line, which is negative 2.8734. And then k is ln of k is equal to the y-axis of that line. And in this case, in order to find the actual k, we will need to take the e on both sides. And doing that, we find that the k is 7.26 times 10 to the negative 7. And then setting the two equations for magnetic field together, krn is equal to the u0 divided by 4 pi 2n divided by r cubed, we find that the magnetic dipole moment u is 3.58 Newton meter T. Here are some statements describing the data that we just collected. These statements basically boil down to, as the distance increases, the magnetic field strength decreases, and as the distance decreases, the magnetic field strength increases. Now we are onto my code, which will be a computational model of the lab. The initial conditions of this code is the magnetic dipole moment, which we found in the previous slide, 3.58. And now we need a function to calculate for the magnetic field from a dipole, which is the code on the bottom. Now here's the rest of the code. On the left are arrows representing various directions that will be needed for this lab. The top two lines represents the directions on the axes, while the bottom four represents the directions perpendicular to the axes. Now on the right is the code used to calculate the magnitude of the magnetic field at a 45-degree angle, using the direction perp that we found in my data collection, which was 0.1955. And here's the result of my code, and the resulting magnetic field at a 45-degree angle at a distance d was relatively similar to the magnetic field that we found in my data collection, and the resulting differences could be attributed to human error. Here are the assumptions and possible errors we could have made in this lab. Errors. Other magnetic objects could have messed with the magnetometer data. And the second, the location of the magnetometer may have been incorrect. And lastly, there could have been human error in collecting the data. And now the assumption that we made in this lab was that the bar magnet acted as a magnetic dipole. Here are some questions that we're going to answer. Had we not orientated our phone at the beginning, the Earth's magnetic field would have messed with the data, skewing the results. And had we stuck two identical magnets together, the field strength would double, but the direction of the magnetic field will remain the same.